Yeah, good morning, all. I'm audible?
Yes, sir.
Yes, sir. Happy Ram Navami to all. Anand, sir?
Hello. Yeah,
Yeah, good
I can
morning, sir.
hear.
Yeah,
Happy
yes, sir.
Ramanavami. Good morning.
Yeah, thank you, sir. Thank you.
Yeah.
So we will wait for some more participants, sir. Nearly 50. So we'll look for some participants.
Sure.
Shall we start, sir?
Yeah, I'm good.
Yes.
Yeah.
Yeah, few seconds, sir. Sir.
Can I start presenting or?
Yeah, just a minute, sir. Just.
Okay.
I know, late. I know.
Good morning, dear participants and invited speakers. On behalf of PPG College of Arts and Science, we welcome you all for the second day International Conference on Energy Conversion and Storage. Now, I would like to invite Dr. S. Harikrishnan, Organizing Committee, to introduce today's chairperson and the next session invited speaker, Dr. Anupam Roy.
Thank you. Warm welcome to this session. I invite Dr. Anand B. Puthia for a seminar on the use of 2D materials as electrocatalytic and supercapacitor electrodes. Dr. Anand received his BS from Calicut University in 2008 and MS from Cochin University in 2010, both in physics. He received his PhD in physics from Cochin University in 2016. Following PhD, he worked as a postdoc in TIFR for 1 year from 2016 to 2017. Thereafter, he joined Rice University with Indo-US Fellowship, and currently he is working there as a postdoctoral research associate. He is a member of several international communities like MRS, SPIE, ECS, received several awards, and served as a referee to many international journals. His research interests include dielectrics, piezoelectrics, magnetism, carbon materials, two-dimensional oxides and sulfides, and applications in sensors, actuators, energy conversion, and storage. He has 3 invention disclosures to his name, delivered several invited talks, published a book chapter, and over 30 research papers. All of them are in prestigious journals like Nano Letters, 2D Materials, Advanced Materials, Applied Physics Letters. I personally have followed several articles from his group. Dr. Anand, welcome.
Thank you, Dr. Anupam Roy. Thanks for the nice introduction. And probably I can go to the session, right? I can share the screen and whether my screen is visible.
Yeah.
Okay. Good morning. Here it's evening, but still good morning, and thank you for this opportunity to share a few of our research and some thoughts on how 2D materials can act as a supercapacitor electrode, basically an energy storage device. As we know, we are all going through an unprecedented situation. This pandemic is not seem to be over. There is a second rage is going on. Hope everybody is keeping safe, and through vaccination, probably we could eradicate this situation soon. And it's an opportunity, right? Like we can communicate through online platforms like Google Meet, Teams, and Zoom, which is a blessing. At least we could still continue the academic activities like conferences and a few other discussions that can be still done, which is a good thing. And I'm going to the technical session. So the title of my talk is 2D Materials as Supercapacitor Electrodes. A little bit about Rice University. It is set in the heart of Texas, Houston. It's a small school and it's a private university, but it is really famous for its leading research activities and a lot of impactful alumni from here. Even the fullerene has been discovered in Rice and awarded Nobel Prize for that discovery. And Rice is famous for some sports activities as well. And if you look at the facts, it is one of the top 5 private university in US, and Rice hosts a lot of international community here, and the faculty-student ratio is around 6:1, and top 20 in US, and it has a lot of resources. And if you look at the mission and values, we can actually read Rice as 3-4 terms like responsibility, integrity, community, and excellence. So we can feel Rice like that. And I'm working with Professor Pulikala Majan. He's a famous scientist in the field of material science and nanotechnology. He was involved in He was involved in the early research of carbon nanotubes, and he's a pioneer in that field. Later, after the discovery of graphene, there are a lot of research happened in the field of 2D materials. There are several fields that he is interested in, and our group is literally big always. 50 people are working together for the advancement of materials that have several applications in different fields. If you look at his accomplishment, he has been cited heavily. He's above 1 lakh citations, and H index is around 200, which is a remarkable number and an achievement for scientists in this field. And he has given a lot of invited talks in US and abroad. And he has been awarded several prizes, and he is a founding chair of material science department in Rice, and he is a well-wisher of Indian research as well. So he travels to India a lot, and he delivers a lot of talks in different parts of this country, IITs, IISc, and he visited Kerala several times because he is basically from Kerala, a nearby state. Having said that, let me briefly discuss the outline of my talk. So I hope everybody will appreciate if we start with the fundamentals of what we are discussing and then goes to like deeper area of it. So I'll start with like what is capacitance and how they are classified, what is the time evolution of different capacitors, and how the capacitance is getting increased from a conventional ceramic capacitor to what you call supercapacitors, and a lot of research is going on in this field these days, and what are the different sorts of capacitors and pseudocapacitance, etc. And we will transit into 2D materials, and I will specifically look into one particular research problem, how functionalization of a graphene nanoplatelets could change the properties like supercapacitance behavior or the electrocatalytic behavior with which we can split water into hydrogen and oxygen, probably the next generation fuel like our fossil fuel these days. So capacitance is something basically we can identify it as the ability of a system to store an electric charge. How we can store charge? That's an interesting question. Whether if you have of course you need a conductive plate so that the electron can move, at least, right? It should be what you call a conductor. But if you have a single conductor, whether we can store charges? No. If you introduce more electrons to that particular region due to this Coulombic repulsion, you cannot accumulate more charges at that point. Basically, the whole system has to be neutral all the time. So if you inject more electron, it will be repelled and you may not have more charges at this point. And as a whole, the system is under equilibrium. So with a single electrode, you cannot store any charge. But what happens if you bring two conducting electrodes together? So the ultimate goal of the system is to get an equilibrium state. So if you introduce more charges here, electrons can be depleted from here and it can accumulate here. But still, because of this, so if electrons moves here, you have a net positive charge here, and if it is accumulated here, you have a net negative charge. But if you have two electrodes comes together, the whole system as a whole is electrically neutral, and probably you can accumulate more charge, one type of charge on one side and another type of charge on the other side. Still, the whole system as a whole is neutral, but you have excess charges on either side, which is basically a potential difference. And if you connect this thing to a particular circuit, this can be discharged to that circuit, and basically it can do a function. So this is the basic principle of charge storage. Bring two different conducting electrodes and keep it together and apply voltage across it so that you can push excess charge on one side and another type of charge on the other side. This is how we store charges in a parallel plate capacitor. And what are the parameters that affect, or how we can improve the charge storage capacity of this particular system? If you bring the two plates together, basically it's all electrostatic interaction, right? So then the charge neutrality can be achieved in a better fashion because the interaction length is smaller. So you can include more charges in the two plates. Otherwise, if you increase the area of your electrode also, you can actually accumulate more charges in the system. So these are the two parameters, physical parameters, we can play with to improve the charge storage mechanics. So one is area of the electrode, one is the separation between the electrodes. And other way to improve the charge storage capability of this parallel plate system is introduce a dielectric material in between. Dielectric material is, we all know, like if you apply an electric field across it, they will polarize against the applied field. So you have a net positive charge on one surface and net negative charge on the other surface. So this will also help to reach the electrical neutrality with excess amount of charge in one plate and opposite charge on the other side. So the ultimate goal is to make the electrical neutrality as a whole, but separate the charges as much as possible. So with the separation, area, and introducing a dielectric material in between, you can literally increase the capacitance of that particular system. And let's look at the age-old ceramic capacitors. They are still heroes. They are in most of the electronic circuits to act as a capacitor, because which is dry, easily integrated into almost all the electronic circuitry these days. And if you zoom in at the electrode-electrolyte interface, this is how a ceramic capacitor looks like. You have a positive electrode and a negative electrode and a dielectric medium in between. And as soon as you apply a field, this is how the whole system behave. You will have a net negative charge on one side, net positive charge on the other side, and dielectric medium polarized like this, which will facilitate the excess charge storage on either side, which in turn produce a potential difference across it, and that can function as a charge. And if you look at how electric field varies across these two electrodes, electric field is constant. If you look at the voltage, it goes from high voltage to low voltage if you go from positive to negative electrode, and this is the separation between the two electrodes, D. And if you do a simple math, like we identified that we can vary the capacitance with the separation between them, which is inversely proportional, and the area, which is directly proportional. So capacitance is directly proportional to A, inversely proportional to D, and the proportionality constant can be converted using a dielectric constant of the medium that separates these two medium. And this is a specific thing for different materials. For air, vacuum, it is 8.84 into 10 raised to minus 12. And if you bring some other medium, this is slightly higher. And you can calculate the capacitance, which is 0.221 nanofarad, right? Which is a small number, but this is still acts as a capacitor. And we can see what is the limiting factor here. You have two electrodes and you cannot bring them closer. You cannot reduce D after a limit, right? That is limiting the charge storage capacity here. And you can't increase the area to a large level because you have to incorporate this into a small miniature circuits and etc. So these are the limiting factors. The only thing we can improve probably is decrease the separation so that you can increase the charge storage. And that idea actually brought into the electrolytic capacitors. Here you have still two electrodes, but what we have done is like you have an electrolyte in this system. So basically, you will take a polished aluminum, for example, one side, and cast aluminum on the other side, and you put some electrolyte into the system. So this electrolyte, when interact with the polished aluminum surface, it will produce a small, thin layer of oxide across it, which is our dielectric now, which is of the order of few micron or below a few micrometer. And if you apply charge across it, this is how the charge formed at the interfaces. Positive charge here, and you have aluminum oxide dielectric, and then negative charges from the electrolyte will accumulate here. So this is a capacitor. And probably you will have a small capacitance at this layer also, but that will be slightly less compared to here, because the separation between what you called here is of the order of 0.013 micrometer or something. So when come to electrolytic capacitors, we have reduced the separation between two electric charge layers so that we can increase the capacitance. Another thing is like electrolyte will be wet the large area of the material also, right? So we have increased the area of the electrode in principle. Also, the separation between the two charge storage layers is reduced a lot. This is how capacitance jumped from nanofarads to microfarad, which is 10⁶ increment, which is very impressive. And if you look at electric field variation and voltage across it, it goes like this. And this is this is interesting. Now, what will happen if you bring two electrical double layer system on either side? That's actually comes out as a supercapacitance concept, which is an evolution, right? Like start from ceramic capacitors, we identified several parameters and how you can improve this thing. But here you have a liquid system in the system that makes it not that compatible for all the systems, because you need a proper sealing and etc. That actually reduced the whole compatibility in some of the circuits. But still, if you have more capacitance, you can need more capacitance, and some compatible areas you can use electrolytic capacitors. And since you have two electrical double layers here, if you connect two capacitance series, the effective capacitance goes like this. And then comes supercapacitor. Make the same situation either of the sides of the electrode. So what we will do, we will take two electrodes, separate this two electrode using a dielectric or a membrane, which is an electrical insulator that avoids the shorting between them, and put electrolyte. Both sides you will have a Helmholtz layer or charge separated layer will form. And if you look into it, the separation between the two layers here will be a solvent molecule. Basically, as you know, if you dissolve some salt into a solvent, most of the easily dissociated salts, sodium chloride or what you call H2SO4 or whatever, H will be solvated by the solvent ions, and the other what you call the counterpart will be also solvated, or they will stay, because the number of solvents that's solvate will be slightly different, depends on the size of the cation anion. But in any case, if you apply electro voltage across it, what can happen is here it will be negative and positive charge will align here. In between, we will have the solvent molecule. As we know, the solvent molecule size is of the order of Armstrong, right? I mean, less than a nanometer. So the separation between the double layer is like further decreased to Armstrong level. So you should definitely expect a bigger capacitance here. So 10⁻⁻⁶ microfarad to farad range. So here the separation is reduced to Armstrong levels from few micrometers. That's make the charge storage capacity to a very big value. 1 farad is not a small number, it's a very big number with which you can charge. I mean, you can store a lot of charge. And if you can somehow increase the electrode area, that would even add value into it, which will increase the capacitance to magnificent values and very magnified value. And we have to really careful here. We have a liquid system. So again, the system would like to get into neutrality. So if you apply charges, this layer will come and first layer of positive charge will form, and that will actually disturb the neutrality of the whole electrolyte, right? So there will be a what you call, let me look into it. Like there are several models that to explain this double layer formation. So you will have a first layer solvent between and net positive charge here, and then while going to the bulk of the electrolyte, slowly they will distribute further and you will find an electrical neutrality. So if you look at how voltage varies across it, starting from here and goes down slowly when you go to the bulk of the system. So you can ideally, if you zoom into the electrode-electrolyte interface, you will see some situation like this. You have a positive charge, immediately negative charges, then net there will be a negative excess layer, which is distributed or diluted, and then it goes. And when you go to the bulk, again, it will be positive or negative equal. And there are different people studied this system, and they have actually quantified how much charge will be there, how much it is distributed, etc. And if you are interested in it, please try to read some of these books. Even I think I have also contributed to one of the book which describes this mechanism in detail. And let's see how the electrical double layer capacitor works under a discharge condition and the charged condition. So this is the initial situation. You have electrolyte, solvated ions is normally distributed everywhere, and there is no polarity on the other side. And if you have, as soon as you apply a polarity, one solvent layer formed, and then if this is negative, positive charge will come here, and the negative charge will come here. So you produce basically two capacitors, right? Minus plus here, plus minus plus here. This is two double layer capacitors are formed. And this is how, if you zoom into the one electrode, positive charge, solvent molecule, negative charge. And if you look at the volt potential variation, positive to negative within a small distance scale. So that's produce a big voltage difference. And over electrolyte, there is no much charge difference. So it slowly goes like this. And if you, usually we do this, right? If you see a system, can we display it in a quantitative or in a scientific way? We usually describe it in terms of equivalent circuit. So we will identify the resistance of this electrode as Re, electrode resistance, and the capacitance here, capacitance I formed here. Ri is mostly the electrolyte have also some resistance, which is ionic resistance, ionic conductance resistance. It will be normally smaller, how resistive the whole system for ionic diffusion, etc., mass transport, etc. That we will identify as Ri, and then other capacitor layer C2, and finally this other electrode. And this is how a supercapacitor can be described: two capacitance layers, series resistance, etc. And as you know, if you apply voltage, these double layers will form, and there is a intrinsic tendency that they can relax back, right? If you keep for some time, there will be some leakage. We used to identify in terms of leakage current, which is normally higher for supercapacitance, because you are keeping these charges intact on the surfaces, but they have a natural tendency to diffuse back and into the bulk. So battery, the case is slightly different. I mean, probably that is out of scope now, so I'm not going into that too much. And I hope several people, most of the community, appreciate what is this curve, how this curve can be described. So we know, right, the capacitance is C equal to Q by V, or Q equal to total charge is total charge stored is directly proportional to the applied voltage, and that proportionality can be removed using the proportionality constant C, which is specific to different materials. So if you see, when you do a CV, what we will do is like you are scanning across a voltage, right, or a constant voltage, I mean, scan rate dV by dt, which is always constant. So each second you are applying a voltage like this, and if you convert that into Q by V, and you know the current you said, or the current that comes, and you know the time scale at which this is, I mean, so I into T by that voltage. That is always same, right? Because you are doing CV with the constant voltage steps. That's why you are getting the change in current is more or less same. So Q by V is always constant during the whole scan. That's why you are seeing a square like curve like this. So let's split at each point like this. And if you find even if you see the current also, this is the same. It's always remains constant. And capacitance, if you draw, it will be like this. And you can calculate capacitance to different ways. At the end of the day, what we are measuring is the total charge over the applied voltage. You can attain this value through cyclic voltammetry, charge discharge studies, etc. in a convenient fashion. Whatever facilities available, you can do that. And if you look at the battery and supercapacitor charge discharge, the variation of voltage over time is like battery has a plateau, right? The discharge plateau. So voltage won't change for a prolonged period of time. So in principle, we can say the charge is infinity. And supercapacitor, this variation of voltage is sluggish, not as low as battery, but in between. So we will see a discharge like this. And for electrolytic or ceramic capacitors, voltage will change quite quickly because the charge storage is very less and the mechanism is different. So this is how, if you plot the voltage variation over time, battery is infinite, supercapacitor is moderate, and electrolytic or ceramics are transient. It happens very quickly. And what are the parameters here, right? I mean, we used to say capacitance farad per gram, but whether if you put like a 10 milligram of material, only the surface is contributing towards this capacitance, right? So rest of the area is kind of dead weight. So we are not really talking the right story. Probably only the surface material is contributing and rest of them are dead weight. So if you put farad per gram, we don't know how accurate it is, but that's the way we goes with that. But if you can find out the actual surface area per gram, that is more reasonable to talk about. And here comes Nano Materials. They are heroes because they have high volume to surface ratio because their size is very small. And that is actually playing a big role here. And with the discovery of new nanomaterials, conductive and moderately conductive nanomaterials, the field of supercapacitance also really progressed a lot because of such materials that have high surface area per volume. And we discussed about the electrical double layer capacitance, and pseudo capacitance is that you will have a double layer here, and if the charge is transferred into the system, there is no charge transfer happening in the EDLC. But when it comes pseudo capacitance, the charges here will be adsorbed onto the surface and it get neutralized. So there is a charge transfer happening, and that charge transferring in the CV will be reflected as an extra peak or hump. We used to say, right, like Faraday and non-Faraday reaction. Faraday reaction means there are charge transfer, oxidation reduction happens. Here it's not full oxidation, it's a partial oxidation I will be discussing shortly. But if it is a normal, nice capacitor, only EDLC, electrical double formation, you will see a nice flat curve. And if your system has like parasitic resistance, your electrode has some high resistance or electrolyte has high resistance, then you will see a slanted curve for a supercapacitor. We used to say, okay, it's a supercapacitor, but have high resistance. And if you have adsorption it happens for some particular type of electrodes, then we will say you have a pseudo capacitance also. So all these things can come together, which will increase the capacitance, but the kinetics is slightly lower for adsorb type reactions because you are adsorbing it and releasing it will be slightly slow. So some sluggishness will be there, but still it is still faster enough for better capacitance. And as you know, 1 mole of electron will have Avogadro number of thing, and this is the maximum amount of charge that can store by 1 mole of electron. And in a pseudo capacitive reaction, how many electrons are involved in the partial oxidation reduction? Accordingly, you can find out the theoretical capacitance of the material. We never reach theoretical capacitance in the experimental cases because there are some other parameters also playing the role here. And if you have a nanomaterial, the good part is that all the charges can come to the surface and they can solve it very easily. And the diffusion length, the exposed surface interface area, they are very high for nanomaterials. Basically, the nano size effect. And if you look at pseudo capacitance, it's not a full reaction. At the surface, if you have a high atomic number ruthenium oxide like structures, the outer electrode configuration you have a nucleus, but since they are big enough, the crosstalk between the outermost electron and the core nucleus is slightly lower or very much screened, so that there are chances this system can actually partially oxidize and reduce on the surface even without the total charge transfer. We used to say partial transfers, so that you will have an electrical double layer plus charge transfer resistance. Capacitance comes out or charge storage comes out, and there are some other material where atoms will intercalate into the system. That is a slightly battery-like and still fast enough. Some structures will allow fast kinetics. And if you see the CV, this is the pseudo capacitance on ruthenium oxide, and this is the intercalation-based capacitance. You will see well-resolved cyclic voltammetry oxidation reduction curve for intercalation. And for partial oxidation reduction, you will see these small things. And this is a stochastic process, right? Charges will go adsorbed and they will come back and then go again because it's a partial oxidation reaction. You might see a flat curve for even pseudo-capacitive material, but what is happening inside is like multiple oxidation reduction. And if this frequency is very fast and they may not be resolved enough, and you will finally, or our instrument cannot read that specific oxidation reduction thing, but it will get an average current out and something like that. And let's try to classify. Okay, this is a broad supercapacitor class, and three different things, right? Electrical double layer capacitance, pseudo capacitance, and if it is intercalation, we used to say hybrid. If you have both, and then electrical double layer, pseudo, and hybrid. And if you look at the materials, mostly nanomaterials because of high surface area. Activated carbon means carbon with activation means it has more exposed to surface area, and carbon nanotubes, graphene, they are typical high surface area materials. And If you want pseudo-capacitance or partial oxidation reduction, you might want to go for some other materials like conducting polymers or metal oxide. Moving forward, I mean, this is just a time scale of different things, how capacitor is at what time, electrochemical capacitors, batteries, etc. And comes to the world of nanotechnology, you have different types of nanomaterial, depends on the dimension of confinement. 0D materials, it confined all the way, all directions, and the electronic state changed in that way. And nanotubes, one dimension confinement. Films or codes, two-dimensional materials, which has a confinement in only in one direction. And then crystals, 3D, there is no confinement in every direction, which is good enough. And if you look at the behavior of a material that can be used as a capacitor, means it's not fully we don't want like metallic-like material, right? If it is metallic, the what you call the charge potentials at individual points is really less, because it will be an average thing, because a highly conducting sample, it's band-like charge distribution at the surface. So we want a moderate conductive material that can accumulate charges at individual points so that you can have a higher double layer, etc. So that's why if you look at the materials that used for supercapacitor, their activated carbon is not that conducting, still have a good surface area. So sometimes you might want to add conductive additives to connect the non-conducting materials through conductive additives so that the charge can go to all the areas. And that was the kind of bottleneck associated with high surface area material. Their conductivity is very poor, so that even electrons cannot come from current collector to the material. And with the discovery of enzymes, they are still high surface area, but still better conducting than conventional activated carbon or some other materials, which is like titanium-based nitrides or carbides like structures. They have a slightly better conductivity, but at the same time, high surface area and everything, moderate thing. So this is the hero in the field of supercapacitance now. Enzymes, they are showing much better behavior than activated carbon or conventional thing. And even if you think about 2D materials, we can imagine that it has a higher surface area to volume ratio, and it's one layer. The whole material is contributing towards the capacitance. But if you count the number in one layer, the number of atoms, these are very less, right? So the total charge stored will be also less. Maybe per unit volume, it will be very high. But if you think for practical applications, how much graphene layer would need, or how much, it is still a one layer material, right? So how much area would need for the storage of charges that can be used for practical applications. So there is a trade-off, right? So you might want to add two more, and then they will stack together, and it's no longer graphitic. So few such things are there. So I would say the ideal material of a supercapacitor, probably graphene nanoplates. You have multiple layer of system. So I am now slowly trying to dive into a particular problem instead of a general concept. So graphene is like well explored for several things, right? And it's good for everything in some sense. There's a holy grail or a holy grail material for the last 2 decades for most of the researchers in the field of material science and some other things. And it opened like a lot of new fundamental physics kind of stuff, and people can study. It's a nice test bed for several other things. Though practical applications are still far away, but enough research will bring this material. So basically, production and reproducibility is a bottleneck, because you are making a thermodynamically not stable structure. Two-dimensional structures are not thermodynamically stable. You either need a support, or you need to hang it, or they will corrugate or make rolls, right? So there are some intrinsic problems associated with that. That's why it is taking a little longer time to come into the real-time applications. So what I am trying to see here is like, okay, you have a graphene nanoplates. How good these samples are for basically energy storage or catalytic activity, which splits water into hydrogen and oxygen. Hydrogen will be probably the next generation fuel if we can store hydrogen nicely. Or our normal fossil fuel pumps can be converted into hydrogen storage like fuel, and it would be easy transition. Of course, there are other opportunities out there. I am not saying that they may not happen, but if you can make hydrogen as a fuel, that would make life easy, because the existing infrastructure can be used for the storage of hydrogen in some sense. So what we are trying to look is like how functionalization of this graphene nanoplates change their behavior towards electrocatalytic activity as well as energy storage. So if you think of graphene nanoplates, that it's basically few layer of graphene, and everything will have edges, right? And whenever it comes to CNT or graphene, we will have a what you call armchair like what you call edge and zigzag like edge, and the electronic distribution will be slightly different. And if you look, zigzag edge will be more active because it has more localized electrons. Here it's all properly bonded to the nearby atom, so we don't have enough electron available for the reactivity. But if you are looking into this problem, we don't know what edge each nanoplates have, so we probably need to look at the both cases. So we can functionalize these edges with different what you call functional groups, COH, ONH2, N2F. These are all like kind of famous for improving the catalytic activity, at least in the literature, and improving the charge storage capacitance, etc. So what we tried is like systematic way of functionalizing the system and see which is detrimental, which functionalization is detrimental, which functionalization is can improve this property. Or if you have capacitance is charge storage, what you call the electrocatalytic capacitance, we don't want to attach the hydrogen atom to the system, but it should come to the surface and it should release as soon as the charge transfer happens. So these are two different things, and we are just wondering whether these two things are complementary or not, and the results was really interesting. So we gently functionalize, because if you functionalize with like what you call heavily acid kind of medium, it will break several things, right? And we never know, some basal planes, atom vacancies, those things, and so to study actually the actual variation, probably we need to what you call functionalize gently. So we used a plasma type of approach to functionalize it, so that the whole structure will stay intact and impurity levels will be very high. So if you go for Hammer's method and some other kind of heavy acid treatments, probably we will have more impurities that would reduce the hand on the system, or how you understand the system probably not the same what is the actual system is, right? I mean, at least we expect something, but the actual system will be slightly different. And we characterized, there are several techniques to characterize materials, starting from XRD, Raman. Raman is specifically good for 2D materials, because as soon as you confine to 2D, the in-plane vibrations dominate to the what you call out of plane phonon modes, right? So you can identify whether your system has a two-dimensional confinement or not, where you will see in-plane vibration phonon modes intensified. And if you look in the 2D material research, Raman is the major tool to characterize them. And if you look at FTIR, you can see the molecular fingerprints, how much things you attach, functionalize, those peaks will show up. You can do that thing. And you should look under microscope, because as soon as nanotechnology, without a nice electron microscopic image, I think nobody will believe, okay, you made a nano system. And electron wavelengths, if you use the 300 electron volt, the wavelength is in the order of few angstroms, so you can see atomic arrangement. And the state-of-art microscope can resolve Armstrong level length scales these days. And there are claims that even you can feel the electron cloud at some point. And that's very fascinating, and it gives us an opportunity to see what is happening in the atomic scale. And atoms are very nicely ordered in a particular what you call crystal structure. We have only 7 crystal orientations possible, symmetric or systematic thing. But still, you can see how carbon atoms are formed in the system. They are what you call sp2 hybridized and bonded each other, and you can see the d-spacing between the layers, which is around 0.37 nanometer in the case of graphene. Here you have multi-layer graphene, right? Graphene nanoplates, and we see we have to make sure that we gently functionalize the system, and we look at the electron microscopy of all these functionalized system, and they are still keeping that particular d-spacing. So which means that they are not what you call, the treatment we have done is not hashed enough to destroy the whole structure. And through XPS, you can actually quantify how much what you call functionalization you brought into the system, in what rate, under the area, under the curve, for each different bonding types. You can actually quantify how much is your functionalization to the bulk structure. You will have carbon more, and how much functionalization you bring can be reduced from XPS. And when we did the Edlc test, basically you make electrodes on either side with the functionalized materials and calculate the capacitance. It was quite interesting. Like pure GNP has one particular capacitance, and if you functionalize, it varies. COH functionalization, it is reduced, and when you fluorinate it, it is increased. I mean, there is a trend that you can see with various functionalization. And when we do the HCR test, basically hydrogen will into a radical form and it's absorbed on the surface, and then another hydrogen through charge transfer they will form H2, and then which will basically evolve from the system. And you can basically characterize this thing. People who works on the system know how to do this, but you want to split the water. Usually you want to apply 1.2 voltage across the system so that oxygen and hydrogen separate and they evolve. But if you have a catalyst, you can reduce this voltage window to lower values. That's the whole point of making catalytic material, so that you can reduce the net power or net energy that need to make hydrogen from water. So that's the whole point, right? And here, if you see, sewage functionalized graphene nanoplates is doing a better job, which is splitting water at lower voltage, and fluorine functionalized system is doing a bad job. It is decreasing the catalytic activity. This is our what you call a pristine sample, and it's going left and right, depends on the functionalization. And if you see the charge transfer resistance and few other things, and here also there is a trend. For COH it's least, and for fluorine it is high. And these are some typical parameters people look into when you what you call systematically characterize a catalytic material. You want to know the overpotential, at what voltage splitting happen, how fast it will happen, and what is the exchange current when those kind of things are always there. And we are trying to understand what happened to the system and why this trend, and how can you really explain this trend. And what we want to see is what is the free energy of adsorption desorption. In supercapacitor case also, it is coming close to the surface. In the catalytic surface also, these hydrogen atoms are coming close to the surface. So if it is come very closer and bonded strongly, probably you will get a better capacitance because your d-spacing is less and it's very close. And for catalytic activity, you don't want that much adsorption or attraction, because it should come to closer on the surface and it should be able to transfer the charge, and then it should be released. It cannot get there. So that will make the whole catalytic activity slower. So these are just opposite to each other. And we try to understand both for the case of AMP-share and the zigzag. But I still say zigzag is the most possible configuration, and the reactivity is high in the zigzag edges, because if you look at the formation energy, which is always less for zigzag, because you have an excess electron cloud available for reactions to happen. And all the reactions are at the end of the day electrostatic interactions. So that's the case. And what we study is what is the free energy change during this adsorption desorption phenomenon happen to a system. If a system has a least delta G change in the adsorption desorption, which is a better catalyst, but which may not be a good supercapacitor electrode, because we need two different things for both the cases. And unfortunately, this armchair modeling never followed our experimental results, and which simply means that whatever material we have, it has zigzag edges. But zigzag edge system really followed this is a DFT modeling, followed the trend that we have seen in the experiment. Basically, COH has the least delta G change during the adsorption desorption reaction, which simply say, and which will be a better catalyst, but which may be a bad supercapacitor electrode, because it is not bringing you or which is not adsorbed properly to have a better capacitance. And that was an interesting result. And if you see the trend of overpotential and capacitance, overpotential basically that say how good your electrocatalytic material is, and capacitance say how good your material as a supercapacitor electrode. So here, if you see, it's showing a complementary behavior. If you have higher capacitance, lower catalytic activity, higher capacitance. There will be always anomalies, and we cannot omit them. Probably, which might have some pseudo-capacity effects. We don't know. Some reactions can happen. And GNP ammonia function, this can be easily converted into ammonia, because you have already NH2, and if you bring a hydrogen radical, that can form ammonia, and ammonia gas can be released, which we are not accounted during this course of characterization, because we are only looking for water splitting and this kind of stuff. So this interesting complementary behavior is observed, and we communicated this nanoscale, and they reviewed and they are happy to accept this thing. And it's quite interesting, and it's probably helpful people do work in this field. And I would like to thank Professor Boris Jakobsen and Sharmila, who helped in doing the theory. And I am quite grateful to the principal of PPG College, Dr. N. Muttumani, for organizing this event, for his patronage. Professor Ramaswamy, who is president of Indian Association of Crystal Growth, who is also a patron of this program. And I am thankful to Dr. Mohan Kumar for inviting me for this conference. And thanks for this opportunity. I hope I shared something reasonable. And thank you. I am open for a few questions. And most of this research is funded by Indo-US Science and Technology Forum, who I got a fellowship from this thing, which is a bilateral funding agency, and Army Research Laboratory of US government. And this is our group. And this group is actually big. And during this photo session, few people are missing. So, but still, it's always a big group. A large number of people are working together in different areas. Thank you very much. Thank you for your attention, and I am open for questions, if any. I hope I did on time. I hope I didn't take much.
Thank you, Dr. Anand.
Yeah.
From the participant, if you have any question, you can. So I have one question that for the graphene, the question of stability of monolayer graphene is not that important if you compare it with some MXenes or several TMDs. So how does that affect? Like, for example, MOT to monolayer is only a few hours stable. Then you can think that boron, that the black phosphorus is only a few seconds or few minutes stable in the monolayer form.
Yeah, actually, when we come to the 2D confinement regime, there are different phases, right? 2H, 1T, 1T prime. There are several phases, and as we know, in nature likes the three-dimensional structure, and that's how the whole coordination can happen and charge neutrality can be reached. These 1D structures are thermodynamically not stable at any point, but some structures, layered structures or van der Waals structures, they actually don't have a strong out-of-plane bonding, and they have a strong in-plane bonding. That's why they exist as monolayers. But when we comes to phosphorus or 1T phase of this thing, basically we can simply think that the coordination, the charge structuring is not really stable to at least at room temperature. Probably if we cool down and keep in some controlled environments, they may stay longer, but under room temperature, this thermal excitations and all those things that actually break this particular symmetry, and it might go to some other form of it, or it may corrugate, or it may break down, or it oxidize. Whatever things can happen, simply because they lack symmetry in some extent, if we really say. Yeah.
Any question from other participant?
I think no questions from audience, sir.
Hello. Can you hear me, sir?
Yeah, I can hear you.
Yeah. Sir, how will you choose for that electrode, in particular electrode for this supercapacitor, sir?
How I prepare the electrodes? Yeah. So most of the time, as I said, like high surface area, these things are conductivity will be slightly less. So we used to add a 10% conductive additive, and we might want to add some binder also to attach this electrode onto a what you call a stainless steel plate. Since you are using an acid environment, H2SO4 aluminium foil may not be a good thing, but use a stainless steel sheet and apply this electrode with the binder and conductive additives.
Oh, okay. How will you check for that, sir? If any other instruments are there, find the conductivity of that one?
Basically, if you make a supercapacitor and do an impedance, you will see how much resistive the whole system is. Like initially, when you plot a Niku's plot, the initial separation between the 0 to before this semicircle starts, you will see a series resistance there, right? So that kind of encompasses this kind of thing. But before assembling the capacitor, you can still use a multimeter, right? Like put in a continuity mode and see how much is the resistance across your quarterly.
That is the method is convenient, sir. Because
It should
we
be
don't
okay. Yeah, it should be okay because you would really see it, and it cannot be that resistive, right? You will see few, I would say, 100 ohms to few kilo ohms. Yeah, then that should be a good range. It looks like.
because we are coated in that plate, so
Yeah.
that the performance is accurate performance we cannot be able to measure for that if we are using for a multimeter. So
Yeah.
that I'm asking you, sir.
Okay, I mean, if you want, like, you can use probe stations kind of thing, which do a soft touch on the surface, and you can calculate more systematically. But still, multimeter thing should give you a decent data because it's a bulk sample, right? And you can see. But if your multimeter is better, like use a Keithley multimeter that can measure like microamps to nanoamps current and put a lower voltage and see. Yeah, not just the conventional our household multimeters, but should use Keithley or something like that, which can measure around nanoamps current, which will give you an accurate thing. And try to use a 4-probe measurement technique that would avoid the contact resistance when you do this thing. So
4-4 method also you have to use. Okay, sir. Okay.
yeah, that would give a better picture, looks like. Yeah.
In the 4-bore method, we have to simultaneously we have to increase the voltages and current also, sir, it will be vary. Okay, if you are coating for like a thin film in that electrode, okay, we are getting for that the output is what is that the voltage increases, the current also gradually it will be increases.
Yeah, it should be resistive, right? Ohmic, mostly ohmic, because it's a conductive sample. Yeah.
Okay, thank you, sir. Thank you.
Not as a supercapacitor. I am saying just electrode. You made an electrode, you are capturing it.
Yeah. Understood.
Yeah.
Okay, sir.
Yeah.
Thank you.
Any other question? Yeah. If not, then let's thank the speaker. Thank you.
Thank you, Anand, sir.
Yeah, thanks again. Thanks.
Thank you, valuable time with us.
Yeah. I hope, wishing all the best for the rest of the day and stay safe. We are.
Thank you. Yes, sir.
Yeah.
Thank you, sir. Thank you.
Yeah. Thank you, Dr. Roy, for attending the session. Hope to meet you if you are around.
Yeah, sure.
Yeah. See you.
Bye, sir. Thank you.
Sorry. Bye.
Sir, are you okay, sir? Are you presenting now?
Yeah, I'm just trying to
Yes.
share my screen.
Yes. Okay. Right, sir?
Yeah, can you?
You have time up to 11:20, sir. If you need more time, you will take 10 or 5 or 10 minutes.
Yeah. I'm just trying to start my presentation, but somehow
So if possible, send your present mail ID, sir. We will share.
Yeah, I'll send it to you.
Mail me, sir, please.
Yeah, I just sent it to you.
Okay, sir. I'm looking at it.
Yeah.
Sir, just a minute, sir. I received your mail, sir. Anupam sir, can I share?
Yeah, sure. Yeah. Thank you. Thanks for the opportunity. I'll try to keep my presentation very brief, and I'll talk on the fractal growth of MOAC2 using chemical vapor deposition. So the next slide. So first, what are these layered materials and why they are very important? So these are basically lamellar structure, consist of two-dimensional units, and in plane they are strongly bonded through covalent bond that gives these materials the required structural stability. And then out of plane they are weakly bonded through van der Waals bond, and that's why these materials can be easily cleaved. And usually the cleaved layer doesn't have any dangling bond, so we can make multi-layers with very sharp interfaces consist of different type of layered materials. Like we can use the metallic graphene, then semiconducting transition metal dichalcogenides, then insulating HBN, kind of that. And usually they are hexagonal in structure. And among the most studied 2D materials other than graphene, transition metal dichalcogenides have attracted recent attention, and so they are mostly the chalcogen atoms used are sulfur, selenium, and tellurium. And these layered materials are comparatively new to draw attention, and they have several applications due to their unusual physical and chemical properties. I'll show more in my next slide. So I'll talk about transition metal dichalcogenides, and they belong to the special family of 2D materials that have been thoroughly investigated in recent years due to their unique, for example, unique thickness-dependent properties. They are direct bandgap material when in monolayer form. When in multilayer form, they have the thickness-dependent bandgap. So you can understand that they have several applications like in optical and electrical devices, energy storage, gas sensors, etc. So most of the 2D materials research are conducted on the flex exfoliated from the bulk samples. But large area growth is very necessary for device application, and still an optimized growth method is required. We need highly crystalline and pure films for high performance devices. We need large area growth for manufacturability and layer thickness control for device functionality. To achieve all these, two mostly reported growth methods are molecular beam epitaxy, MBE, and chemical vapor deposition, CVD. And out of these two, CVD has been so far has been most promising in growing large area TMDs with quality that are almost comparable to the exfoliated bulks. So in the next slide, we previously reported for the first time the hexagonal MOAC2 and MOT2 growth via molecular beam epitaxy, and you can see sharp streaks in the reflection high energy electron diffraction pattern. And then the characteristic Raman peaks, a band gap of about 1.55 eV in photoluminescence, and good stoichiometry in XPS. So all apparently predicts a high quality large area growth of these materials. However, when we look into the electrical properties, we see that the variable range hopping mechanism is dominating the conduction, indicating that there are several defects in the grown film, and it is proved through transmission electron microscopy, where you can see that there are lots of defects and dislocations present. So the issue in molecular beam epitaxy is that we have a very high difference in vapor pressure between the metal and the chalcogen atoms, and that's why the overall growth window becomes very narrow, and it becomes very difficult to have fine control over the flux in MBE growth of TMDs. However, for other 2D materials like the topological insulators, Bismuth-based topological insulators, MBE has proven to be one of the best growth methods. But for TMD, so far, several research groups are working in this area, including us, and we are still searching for a sweet spot where we can avoid these issues. I'll now discuss the other growth method, chemical vapor deposition, in the next slide. So the most widely used method for growing TMDs via chemical vapor deposition is the atmospheric pressure CVD. And as the name suggests, this entire process takes place under ambient pressure. And solid metal oxide, MoO3, and chalcogen powders, here selenium, are used as the precursors, and growth occurs at very high temperature, usually above 750 degrees C. As seen in the schematic here, the growth substrate is placed face down on an alumina crucible contains the metal oxide powder. The chalcogen powder is placed in the upstream region away from the central heating zone and heated using a separate coil heater. And an inert carrier gas, usually hydrogen and argon, are used. That usually carries the precursor to the growth substrate and carries the reaction products out of the system via the exhaust. So in the next slide, I'll focus in this. I'll keep the presentation very short, and I'll focus mostly on our recent work where we studied the growth more systematically. So it is observed that CVD growth often produces different morphologies. So in this work, we provided an in-depth analysis of the underlying growth mechanism corresponding to different morphologies and an optimized condition to achieve uniform morphologies of each type. We observed that the change in growth mode from 2-dimensional to 3-dimensional can be altered with selenium flux. So in the next slide, I show that in the optimized growth condition, that is at 900 degrees C, we get compact monolayer, triangular, or hexagonal MoSE2 domain. And you can see from the optical micrograph and atomic force microscopy images and good Raman and PL characteristic about 1.55 eV band gap and uniform band gap in the PL intensity map. So now the interesting thing is in the next slide that here I show the effect of growth temperature and the metal flux that can influence the growth morphology to deviate from the compact triangular or hexagonal modes. So first, at the 900 degrees C, the growth mostly is single crystal, triangular, or hexagonal monolayer MoSE2. And as the growth temperature is reduced to 750 C, the second image, you see that the compact structure of MoSE2 domains ramify into fractals, as seen in the ACM images. So the structural transition we attribute to the difference between the rate of adatom attachment to the edge of the growing aggregate and the rate of edge diffusion. So after arriving on the substrate surface, adatoms randomly diffuse until they reach the edge of a growing domain, and the atoms already attached to the domains or the atoms that attach to the domain try to diffuse along the perimeter to find the thermodynamically most stable configuration of its 2D crystal. And this results in compact triangular or hexagonal domain. Now, at the low temperature, the edge diffusion is highly suppressed, but the incoming atoms continue to attach to the domain edges predominantly via diffusion limited aggregation process. And since there is no effective reshaping due to reduced edge diffusion process, the compact domains generally branch out into fractals. And the fractal dimension calculated from the fractal structure grown at 750 degrees C is is about 1.67, as you can see in figure G, which is very close to the 2D DLA fractal dimension, which should come around 1.7. So this shows that the growth at 750 degrees C follows mostly DLA mechanism. Now branching is also observed. Sorry, the previous one. Yeah. So the now we see figure E and F. So where we have grown the film at 900 degrees C, but with higher flux, and we observe that branching, even in this case, with the increasing flux of metal precursor, and here all other experimental conditions were kept fixed as the growth of 900 degrees C. Now, as the metal flux increases, the adatums that arrive at the domain edge, the rate of adatums that arrive at the domain edge becomes higher. So now, although the edge diffusion still takes place at elevated temperature, it may not be sufficient to ensure the rearrangement of all incoming adatums to achieve a stable triangular or hexagonal configuration, and hence the compact structure will ramify. And you can see that the needle-like central branches indicate the preferred growth directions. So higher metal flux increases the number of preferred growth directions, and the high temperature regime promotes the anisotropy of the edge diffusion. The adatums, in addition to the attachment to the edges, now also prefer to diffuse along the lowest energy diffusion paths on the substrate, promoting the branching and leading to dendritic domains. The branching prefers the three, as you can see, that it prefers the three crystallographic orientation of a hexagon, shown as the red lines. And this indicates that the growth still maintains the 6-fold symmetric crystallographic structure. And because of its preference to a specific orientation, the growth mechanism can no longer be solely explained via diffusion limited aggregation model, as that would predict a growth along random directions. And you can see the fractal from the fractal dimension calculated in case of dendritic domain that is shown in figure H, that the fractal dimension is a little bit higher. It is about 1.8 to 1.82, and that indicates that it is that at 900 degrees C with higher metal flux, the growth is not random anymore. Then in the next slide, I show that using this growth condition, we see the homogeneity across a single batch for each growth conditions. So experiments show that the morphologies are very well reproducible, and if we keep the experimental conditions same, then on the entire sample, entire substrate, we see only one mode of growth. For example, 900 degrees C, we see only the compact mode. We see only the fractal mode at 750 C, and 900 degrees C with higher flux, we see only the dendritic modes. The difference is the nucleation density that is probably arising because as we move away from the center zone, so that will actually the flux will be different if we move from B to G point. So you can see that the number of density, number of islands per unit area is not the same, and it is decreasing as we move from B to G. That is because of the flux. But it shows that the growth is very much reproducible and homogeneous, and it can produce the specific growth morphology at a specific growth condition. In the next slide, I show that when the growth is conducted at higher temperature, 1000 degrees C, we see that 3D island nucleation appears on a 2D domain, and then the island nucleation is more when we have used the higher flux, and that is probably because of twofold reasons. One is at higher temperature we are increasing the metal flux also, and second is at higher temperature selenium atoms will get dissolved faster, and so that can create a selenium deficient condition. And why this selenium deficient condition or the metal rich situation is important, that I will show in my next slide. That the transition metal, yeah, in the next slide. Yeah, right. So the transition metal atoms are much heavier than the chalcogen atoms. Thus, the diffusion of them on the surface are very, very different. To compensate this, the ratio of chalcogen to metal should be tuned in such a way that there are always enough chalcogen atoms to passivate the incoming moly atoms. This can be achieved by controlling the chalcogen environment, or in the CVD experiment that we achieve by changing the selenium onset voltage. So for example, in the left side, when we want to achieve selenium rich condition, we have the selenium onset voltage at 500 degrees C. In the right side, when we want to achieve selenium deficient condition, we have the selenium onset voltage at 750 degrees C. Now, so what will happen when we have selenium rich condition, that each moly atoms that undergo attachment at the domain edges bond with selenium atoms only first, and that will ensure a near Daniel-Emmett free surface formation and strictly lateral growth. On the other hand, in a selenium deficient condition, probability of moly atoms attached to the domain edges to bond with other incoming moly atoms becomes higher because of limited availability of selenium atoms. And this will enhance the chance of metal clustering due to incomplete selenium passivation of moly nuclei that can lead to three-dimensional island growth. So in the next slide, I show that the images on the top in the next one. The next slide. Yeah. So the images on the top show uniform 2D single crystal MOSE2 domain grown in a selenium rich environment. And you can see from the line profile that the height profile and the line drawn on the domain confirms that uniform lateral growth. And the ACM image on the bottom shows that several 3D island nucleation when we have a selenium poor or selenium deficient growth condition. So, and that is again confirmed and verified using XPS in the next slide, where when we do the XPS analysis on MOSE2 grown on, in the next one. Yeah, the next. Yeah. So for MOSE2 growth under two different environment, selenium rich and selenium deficient, we see that when we have selenium rich environment, the integrated peak area of moly 3D and selenium 3D are calculated, and the selenium to moly ratio is about 1:1.98. Which suggests that the grown MOSE2 is reasonably stoichiometric. Ideally, it should be 1:2. But for the case of selenium deficient condition, it is only about 1:1.68. And so it clearly indicates the abundance of moly-rich nuclei and incomplete selenium passivation. In the next one, yeah. So the electrocatalytic activity typically occurs at the edge sides of, in case of MOS2, it is reported that the edge sides and defects of sulfur atoms, that is the unsaturated states and vacancies, that can enhance the HER performance. It is also reported that 1T structures, which is metallic, shows a better HER performance than semiconducting 2H phases. So now dendrites and fractals, as we observe, differ from the ideal stoichiometry and forms metal-rich films. Thus, it will be interesting area for further studies. And we in this work show that using a specific growth condition in CBD, one can produce a specific type of morphology of strictly monolayer thickness. This uniformity over larger area is important not only to reproduce, but also to have applications in devices in any category. So in the conclusion, here I showed that we can synthesize large area single crystal MOAC2 monolayers using CBD, and we have demonstrated the control of growth parameters to tune the morphology and thickness of the grown film. The effects of substrate temperature and the metal flux on ramification of 2D compact structures are explored. Two different branch structures, fractals and dendrites, grow at reduced temperature and elevated metal flux, respectively. Fractals obey the DLA mechanism, and the dendrites with a higher fractal dimension show an anisotropic growth along the three crystallographic orientations of a hexagon. And three-dimensional growth is promoted by incorporating insufficient selenium atoms during the growth, where metal-to-metal bonding due to incomplete selenium passivation can produce islands of multilayer domains. And XPS verified the stoichiometry and chemical composition of the grown film, and we showed that the near perfect stoichiometry of the grown film under chalcogen-rich environment changes to substoichiometric film under chalcogen deficient conditions, which is indicative of metal clustering, and that we believe that require further studies for HER activities. So I acknowledge all the co-authors, Professor Sanjay Banerjee, my advisor here, Saima, Isaac, Hugo, and Osni, and thank you all.
Thank you, Anupam sir. Thank you. Am I audible?
Yeah.
Yeah. Thank you, doctor. Any questions from audience?
Hello, sir.
Yeah.
Yes, sir. That is a very nice presentation, sir. I have two questions to you, sir. First question is, what is that, sir? Your synthesis is a different type of morphologies, dendrite and other things. How will we get for that particular morphology, sir? You are done so much of morphologies, okay? In 900 degrees Celsius and above 900 degrees Celsius. How will you tune that, sir?
So, for example, that I have shown in the homogeneity slide, that when you grow the film at 900 degrees C and keep all the experimental conditions same, you get only throughout the sample you get only compact shape, hexagonal or triangular. Now, when we add more moly oxide, so that we can increase the metal flux. So now keeping all other things same, 900 degrees C and gas flow and all other things same, only by adding some extra metal that would increase the metal flux, and that changes the growth from compact structure to dendritic structure. And to get the fractal structure, that is the random fractal things, and for that you keep everything same, but you have to reduce the growth temperature. That is from 900 degrees C, you reduce it to 750 degrees C.
750 degrees C. Okay, sir. So, and one more question is there. So, in your XPS data, you are measuring for that the distance and the height also. How will you measure for that, sir? In your slide, sir, I don't know which number. I don't know. Distance and you drawn the graph for distance and that sample height. How will you measure that? From SIM analysis, we have measured that.
In the XPS.
Yes, sir. Distance and other things, sir. I forgot.
So in the XPS thing, we only talk about the stoichiometry. We do not measure the height. So we have characterized two different samples. One grown at selenium rich condition and another grown at selenium deficient condition. Where
Yes, sir. Yes, sir.
and from SEM and AFM, we observed that the selenium rich condition is mostly compact shape and strictly lateral growth, that is two-dimensional. But
Okay.
SEM and AFM shows that when you grow in selenium deficient environment, we see some 3D island nucleation onto the 2D domain. And now when we look into the XPS, we find that the selenium rich condition has the moly selenium ratio is about 1:2, close to 1:1.9. That means that it is forming MOSE2. But in the selenium deficient condition, XPS shows that moly and selenium has a ratio of about 1:1.68. That means we have several selenium atoms missing, or that in other words, you can consider it that we have a metal-rich film. So XPS is giving you only the stoichiometry and the chemical composition, not the morphology thing or the microscopy thing. Microscopy is analyzed only from SEM and AFM.
SEM and FM. Oh, okay, sir. Okay, sir. Okay, thank you, sir. Thank you very much.
Yeah.
Hello, Anupam Roy.
Yeah.
Yeah, thanks for a nice presentation. Actually, I have two questions. One is about edges of these dendrites, and second question is just curiosity-based question. So my first question is about atomic structure of these edges in the dendrites. Do you have more details about it? Like what kind of edges, MO, what's the coordination number of MO atoms on the edges of these dendrites?
Right. So this is very interesting question, but unfortunately we tried to analyze it more, but we got some data, but we could not conclude whether it is armchair edge or zigzag edge, so moly terminated or selenium terminated. But it looks like most of the data that we got, we found that it is terminated with moly only.
Okay.
But
the molybdenums are more exposed on the edges, right?
Yeah, so it is probably because that we have used higher metal flux, and that's why there is a selenium deficient kind of condition there. And so moly is attaching. So the probability of moly attaching to another moly is higher in case of.
And in that case, you might be knowing about these cluster compounds on these molybdenum compounds, molybdenum chalcogen compounds, right? There are some cluster compounds. Do you get any such kind of morphology, like formation of molybdenum clusters, molybdenum octahedras on the edges of these dendrites?
Yeah, so the atomistic characterization of the edges are still, we are doing that one, trying to find out, but we cannot means I can say only from the XPS that it is showing behavior that is just like selenium deficient. But yeah, I think it is very important to find out the atomistic view. But unfortunately, we could not do that. So we have a plan to do scanning tunneling microscopy on this sample, so that we can have some atomistic view. But since it is grown on silicon dioxide, so we have to fabricate so that we can have ground. We need to make the ground for the estimate. Yeah.
Okay, then the second question is just curiosity-based question. These dendrite structures looks like ice crystals. Is there any correlation or?
Yeah. It is very similar to the snowflakes. You mean, right? Yeah. So it is very similar to that, and it is very interesting that suddenly they change the growth mode from random fractals to compact, and then the dendrites, and it has a similarity.
Yeah, I have seen these triangular and hexagon types of platelets, molybdenum chalcogenide platelets. But this is first time I'm seeing this kind of dendrites, and these are really interesting structures.
Yeah. And also, I have not shown this one, but we have included that in the paper that we published, that
Hmm.
we also have dendritic structure even in the 3D. So
Okay.
if we have a dendritic structure in the 3D, you can correlate it very well with the snowflake kind of
So
structure.
these dendrites are single layer structures, or it's kind of
So
multi-layer?
that I showed here, I showed here only the like when it is changing the morphology from compact to fractal to dendrite,
Mhm.
entirely the growth is the lateral growth, entirely
Okay.
monolayer.
Okay.
Yeah.
Thank you. Thank
So
you so much.
yeah, thanks.
Thanks.
Thank you, Rai sir.
Thank you.
I think
Thank
no more questions. Any questions from audience? Participants? Yes, sir. Thank you very much, Anupam Rai sir.
Thank you.
Thank you. Spend your valuable time
Thank
with
you
us.
for
Thank
the
you very much.
opportunity. Thanks.
Thank you, sir. Yes.
Bye.